You know, you can spend a lifetime looking up at the cosmos, pondering distant galaxies, but right here beneath our feet lies a story just as epic, a history etched in the very rock of our planet. Today, we're diving deep into Earth's infancy, about 4.5 billion years ago, aiming to unlock a fundamental secret about how our world took shape.
That's right. We've got some truly groundbreaking research fresh out of nature that's giving us a new lens, really, through which to view the chemical composition of Earth's crust way back in the Hadean Eon, the planet's earliest chapter.
Exactly. And we've sifted through the details of the news reporting on this study to bring you the crucial takeaways. Our mission today, to grasp what this reveals about the primordial Earth and, maybe more crucially, how it's making us completely rethink the timeline for the emergence of one of Earth's most defining characteristics, plate tectonics.
And it's a puzzle that has captivated and frankly challenged scientists for decades. The estimated start date for plate tectonics has been incredibly wide-ranging, stretching from a relatively recent 800 million years ago all the way back to the Earth's fiery beginnings. This new research is really shaking up those assumptions.
Okay, so for anyone tuning in who might need a quick overview, what is plate tectonics and why is it such a fundamental process for our planet?
Right. In essence, plate tectonics is the ongoing movement of Earth's massive rocky plates across the hotter, more fluid layer beneath them, the mantle. This constant motion is the engine that, builds our continents, triggers earthquakes and volcanic eruptions, and drives a huge amount of geological activity.
Okay.
What's particularly remarkable is that, as far as our current knowledge goes, Earth appears to be unique in our solar system, and possibly among all the exoplanets we've discovered so far, in having this continuous active system of plate tectonics.
It's like the Earth has a life of its own, constantly reshaping its surface. And this isn't just about the land masses, right? It has broader
Oh,
implications.
absolutely. If we connect this to the bigger picture, plate tectonics is a critical player in the Earth's carbon cycle, which, as you know, has profound effects on our climate. It's also the primary mechanism for Earth to release heat from its interior.
Mm.
And perhaps most intriguingly, many scientists believe that the dynamic interplay of plate tectonics was essential for the very origin and evolution of life on Earth.
So, a planet with a solid, unbroken outer layer, like Mars, wouldn't have the same potential for fostering life through these processes. Is that the idea?
That's the prevailing scientific view, yeah.
Yeah.
Early Earth might have had a more stable, stagnant lid crust, similar to Mars today, or perhaps a start-and-stop version called episodic tectonics, possibly triggered by those, frequent massive meteorite impacts in the early solar system. The big question has always been, when did Earth transition to the continuous plate tectonic system we observe today?
And for a long time, the scientific community has been on the lookout for a specific chemical fingerprint within ancient rocks, hoping it would pinpoint this crucial transition. What's the story behind that fingerprint?
What's fascinating here is a very specific chemical signature observed in volcanic activity at island arcs. Think of the volcanoes dotted around the Pacific Ring of Fire. The lavas erupted in these settings have a distinct chemical makeup, remarkably similar to the average composition of today's continental crust.
Okay.
A key characteristic of this fingerprint is a lower concentration of the element niobium compared to other rare earth elements. You can almost imagine certain ingredients being filtered out early in the process.
Okay, so this depletion of niobium was considered a telltale sign, like a marker.
Precisely. The long-standing hypothesis was that the first appearance of this particular chemical fingerprint in ancient rocks would essentially mark the beginning of plate tectonics. The reasoning was that this fingerprint is a direct consequence of the processes involved in the subduction picture. Two giant conveyor belts of rock colliding, with one being forced beneath the other.
Right, subduction zones.
Exactly. That process modifies the chemistry of the rocks that eventually melt and rise to the surface as volcanoes.
But actually finding those truly ancient rocks from the Hadean Eon, that must be an incredible challenge in itself, right?
Oh, you've hit on a major obstacle. The very process we're trying to understand, the constant churning and recycling of Earth's crust through tectonic activity, has essentially erased much of the geological record from that early period. Ancient rocks older than about 4 billion years are incredibly rare.
Wow.
In fact, it's quite possible that no original crust from the Hadean Eon still exists intact.
Which really puts those previous estimates for the start of plate tectonics into perspective. An 800 million year window is enormous. It suggests they might have been relying on an indicator that, maybe wasn't as definitive as they hoped.
Exactly. And this is where this exciting new research injects a fresh perspective. Starting in early 2024, this international team of researchers from University of Oxford, Curtin University, University of Technology Queensland, and the University of Lyon, led by Simon Turner at Macquarie University, they decided to tackle this from a completely different angle.
So if they weren't digging for these elusive ancient rocks, what was their approach then?
They harnessed the power of computational modeling. Their methodology involved creating sophisticated mathematical simulations of Earth during its core formation period, a time when the Earth's surface was essentially a vast ocean of molten rock.
A magma ocean, basically.
Right, a global magma ocean.
Yeah.
Specifically, they focused on simulating the degree of melting within Earth's early mantle and how different chemical elements would have behaved under these extreme conditions.
That sounds incredibly complex. What were they hoping to, glean from these simulations of the early molten Earth?
Well, their primary goal was to determine the chemical composition of Earth's very first crust, often referred to as the protocrust, which would have formed as this molten surface began to cool and solidify in the Hadean eon. We're talking way back,
Yeah.
almost to the planet's birth.
Okay.
And here's where it gets really interesting.
Hmm?
Their simulations revealed that this earliest crust had a chemical composition remarkably similar, almost identical, in fact, to that of today's average continental crust.
Wait a minute, hold on. So that distinctive chemical fingerprint, the niobium depletion, and the specific ratios of rare earth elements, that was potentially present right from the planet's earliest solid surface.
That's the key sort of mind-blowing discovery. The models demonstrated that during the Earth's core formation, a very early and fundamental process, niobium, was preferentially drawn into the metallic core, effectively removing it from the silicate mantle.
Okay, so it sank down.
Right. Meanwhile, the rare earth elements, for geochemical reasons, tended to concentrate in the magmas that rose to the surface and solidified to form this initial crust. This process naturally resulted in a continental-like chemical fingerprint in the protocrust.
Okay, let me try to process this. So the chemical signature we observe in continental crust today isn't necessarily an indicator of plate tectonics initiating. It might have been a fundamental characteristic of the very first solidified crust as it formed.
Precisely. This has profound implications for how we interpret the geological record. It suggests that finding this specific chemical signature in ancient rocks doesn't automatically signify the onset of subduction in plate tectonics. The fingerprint, it seems, was baked in very early on,
Wow.
and subsequent volcanic activity at island arcs simply recycled and expressed that pre-existing chemistry.
That's a major shift in perspective. It makes sense why those previous attempts to date plate tectonics based on this fingerprint yielded such a broad range of results then. They were essentially looking for the starting gun of plate tectonics, but it turns out that particular gun was already present at the very beginning of the race.
Indeed. And the study also sheds light on the role of those early, intense meteorite impacts. While these colossal events would have undoubtedly melted and reworked the early crust, they wouldn't have created this continental chemical fingerprint. Rather, they would have just remixed and redistributed what was already there.
So while the chemical fingerprint might not tell us when continuous plate tectonics started, could those early massive impacts still have played a role in maybe triggering it? Perhaps by causing some initial localized subduction that eventually led to the planet-wide system we see today.
That's a really insightful question, and the study certainly doesn't rule out that possibility. Some researchers have proposed that these enormous impacts could have fractured and weakened the early, perhaps more buoyant, crust enough to initiate the earliest stages of subduction. However,
But it's not the smoking gun for the continuous process.
exactly. This new research underscores that pinpointing the precise moment when continuous self-sustaining plate tectonics began is far more complex than previously imagined and will likely require entirely novel approaches to investigating the early Earth.
So given this discovery, what are the crucial next steps for scientists? Where do they go from here to unravel the mystery of when plate tectonics truly got underway?
Well, the authors of the study emphasize the urgent need for more sophisticated modeling of the geodynamics of Earth's early crust. We need a much deeper understanding of when this initial protocrust, with its continental-like chemistry, became unstable enough to start the process of subducting.
Oh.
This involves meticulously exploring the interplay of various factors in the early Earth, such as heat flow from the interior, the thickness and density of the early crust, and the viscosity, or how runny or stiff the underlying mantle was back then.
It sounds like they need to figure out the precise conditions that would have allowed the engine of plate tectonics to actually ignite and, run continuously, not just sputter.
Precisely. And the implications of this research extend far beyond just the timing of plate tectonics. This revised understanding of the early crust composition also necessitates a reevaluation of how Earth evolved in its very earliest stages, and how those early conditions might have influenced the eventual emergence of life.
Right, because if the fundamental chemical building blocks of continents were present so early.
Exactly. If they were present so early in Earth's history, it suggests that certain chemical environments conducive to life might have existed much sooner than we previously thought.
And, as the study itself hints, this also opens up exciting new avenues for considering other rocky planets beyond our solar system, doesn't it? If a niobium-depleted continental-like crust is a natural and relatively early outcome of core formation on rocky planets, what does that tell
Well,
us?
what does that tell us about the potential for similar geological processes, and perhaps even the early chemical conditions favorable for life, to arise elsewhere in the cosmos? It raises a really profound question about the fundamental principles of planet formation and evolution.
Yeah.
If a specific type of crustal chemistry is a common outcome of early planetary development, then perhaps the initial conditions for forming continents and potentially even habitable environments are more widespread throughout the universe than we currently appreciate. This could have significant implications for our search for life beyond Earth.
So let's try and bring it all together. This groundbreaking new study published in Nature essentially reveals that the distinctive chemical fingerprint we observe in Earth's continental crust today, it was likely present almost from the very beginning of our planet's history, way back in the Hadean Eon.
That's the key takeaway, yeah. This discovery fundamentally challenges the long-held assumption that we could use this specific chemical fingerprint as a reliable marker for the start of plate tectonics. It now appears that this fingerprint was inherent to the early crust itself, simply being recycled through later geological processes.
And while this fascinating discovery doesn't provide us with a definitive answer to when plate tectonics actually began, it completely transforms how we need to approach that fundamental question about our planet's history. We need new tools, new models, and potentially a whole new way of thinking about the early Earth, right?
Absolutely. This research underscores the incredibly dynamic and complex nature of our planet's earliest history and serves as a powerful reminder of just how much we still have to learn about the fundamental forces that have shaped the world we inhabit. It's quite humbling, really.
It really sparks the imagination, doesn't it? Considering that the basic chemical building blocks of our continents were in place so incredibly early in Earth's history. I mean, what other fundamental planetary processes might have been up and running much earlier than we currently believe?
Mm,
And how might those earlier start dates fundamentally reshape our understanding of the conditions necessary for life to emerge and thrive, not just here on our own, constantly evolving early Earth, but perhaps on countless other rocky worlds scattered throughout the vastness of space?
that's the million-dollar question, isn't it?
It's a constantly unfolding story, this deep dive into our planet's origins, and it's truly amazing to witness how new research continues to deepen our understanding of our place in the grand cosmic narrative.